All right, this is Biweekly Contest 137, starting in 5 seconds. All right, find power of k size subarrays 1. So we're given an array of integers nums of length n, a positive integer k. A power of an array is defined as its maximum element if all of its elements are consecutive and sorted in ascending order. So we define the power of all subarrays of size k. Right, so these are consecutive, these are not consecutive. Results, size results. Okay, that seems pretty easy. We can just kind of brute force this one. And then we'll do for I in range, length of nums minus k. We'll do for j in range. So I just want to see if they're all consecutive. So do I plus 1, k plus 1. Let's do if nums j equals nums j minus 1 plus 1. Then we could do result and max of nums j j plus k plus 1 else result. Alright, so actually no, we can't just check each one. We have to do, so this should be result append. Hold on, let me copy this down here. And this should be append 1. And then we'll keep track of like a valid equals false. Let's say valid equals true, valid equals false, and we'll say at the end, if valid, then we can do this, right? I, and then return our result. Okay, I messed something up. Let's do print I 0, 1, 2, 3, 0, 1, 2, 3, plus 1. And then we'll do print j 1, 2, 3, 2, 3. I plus 1 should be I plus k plus 1. Right, so we get no. I'm missing something up here. So k plus 1. I have to break here. What do I do? So if num is j, I. So start with 0, and then we go to 0, 1, 2, 3. Right. So let's print nums I plus k 3. Okay. Alright, so I am clearly messing something up here. Okay. Oh, I didn't realize this is a medium. Wow, starting off pretty hard. Okay, so we're gonna iterate from every element. So let's just, for now, print I. So we'd want to go from 0, 1, 2, 3, 4. So we want to go for 4. Okay, so that's right. And then let's print, let's do this. I print J J. Okay, so we're going to do 0. So why are we going 0? So I'm not sure why our J's are 0, 1. Actually, I plus 1. If num is j, so 0, 1. So nums j does not equal nums j minus 1 plus 1. But why is this not hitting? Because we're getting j is 1. So we'd have nums j minus 1. Oh, it should be 9. Oops. Okay, so that's progress. For some reason, the second time around, so we're doing 0, 1, 2. Alright, there we go. That was tricky for a Q1. So So let's just run all the test cases and we see. -4, -1, -1, -1. Okay, I think that's good. Okay, so now let's copy this and go to question 2. Let's see if this is the same. There's all these elements. So same thing, but now we just can't do that iteration, right? So basically what we want to do, I think use prefix sum, basically, where, so say our elements are 1, 2, 3, 4, 5, 7. So if we do a prefix, it would be 1, 3, 6, 10, 15, 22. Our k equals 3, right? So basically we want to look at this range of 3. So how do we tell if these are all consecutive, right? So I think we'd have to do something with this prefix sum. So we see this is 6. So how do we tell consecutive? So we can't iterate through all of them, so we have to figure out something where we can know in constant time. So I don't know if the sum can really tell us that. Let's see. Right, so I'm guessing if we run this, the test should pass, but it's just going to be too slow. How do we tell consecutive? So maybe we count the number of consecutive elements. So here we have 1, 2, 3, 4, 5. But then here, this is not consecutive, so this goes back to 1. Right, so then at this point, so here we can figure out, like, if, so we have this range 3, if, say this is j and this is I, if j minus I, whatever the array is, so array j and I equals k minus 1, then that's good, but we also need to know the max. Right, so we also need another way to keep track of the max in this range. So we use prefix, or rather like a pre-calculated array to keep track of if they're consecutive. But then, right, but if they're consecutive, then it just has to be whatever is at j, right? Okay, I think that makes sense. So let's do this. So let's do prefix equals 1 and for I and range nums. I'm going to do this pre. Let's do 1 length of nums. And this should be if nums I equals nums I minus 1 plus 1, then we can do to prefix append pre minus 1 plus 1, else we just restart a new consecutive sequence. Then what we do is we want to start for I at range k minus 1, the length of nums. So what we want to do is we're starting at index 2. We want to find our end equals nums I. Our beginning equals nums I minus k minus plus plus 1, right? So we have, if our I is 2 here, our k is 3, so that'd be negative 1 plus 1. So we have to do if, sorry, this should be pre. So if end minus beginning equals k minus 1, then we can result dot append nums I else append negative 1. Alright, let's try that. That seems like it works. Alright, nice. Maximum value by placing 3 rocks. Oh, we got a hard on Q3. Oh boy. Alright, let's get some paper here. Or rather, get my tablet screen. Leetcode is not playing around with these contests recently. So we're given an M by N 2D array board representing a chessboard. Board IJ, okay, so just a grid basically. Rooks in the same row or column attack each other. You need to place 3 rooks on the chessboard such that the rooks do not attack each other. Return the maximum sum of the cell values for which the rooks are placed. Oh, I see. So it's like we need to, so we're given this board, right? It's M by N. We don't know exactly, like the values here represent this cost or the score rather. So we need to place 3 rooks in anyway. So I'm thinking we could maybe do like a backtracking kind of thing where it's like essentially we're gonna have at most so like basically we place a rook on the board, right? So let's try to draw like a board out here. I don't know why this isn't working now. I'll refresh this. Not sure what's happening. Okay, so we have this. So we have a board, so like this. Right, so like this is 0, 1, 2, 0, 1, 2. So for example, we could do backtracking. So we place a rook here. Let's draw like a little rook or whatever it is, right? And then we could say, all right, so let's keep a set of our, this is our rows, and we'll say that row 0 is occupied, and also a set for our columns. Where we say column 0 is occupied, and basically just do backtracking. So like we go here, then we'll go on to like the next row, essentially pick one column where we can place it, and just add to the set. So we can probably do this with recursion, but I don't think we can. We can't really pass. If we need to do memoization, we can't do it with these sets, right? Because we can't hash a set. So maybe we can just do backtracking where the set is like external. So let's do find max score, right? And then we're gonna have our column, right? We're gonna go by column index, and let's do occupied rows, keep it set here, occupied columns set here. Okay, so then what we're going to do is we're going to go through each row and try to place it there. So basically what we're going to do is say if column index is greater than or equal to for the length of the board 0, right? If you're down at a bounds, it's 0. Otherwise, we're going to do for I in range, length of board. What we could do is say if basically if I is in rows or col index, well, no, we probably don't need this, right? Because we're going column by column, so we just need to check the rows. So then we can continue. Otherwise, what we want to do is we want to keep track of our answer. Let's have it be 0 to start. And then we're going to say our answer equals whatever the cost is of the board. So we'll do board I index. So we need to first rows at I. Then we're going to do find max score and do col index plus 1. Then at the end, we're going to op rows remove I. And just return our answer. And I think this will work, but my concern is it fast enough? Okay, so I got -1. How did I even get -1? I don't know what I did. All right. If the column index is greater than or equal to the length of board 0, right? So if it's out of bounds, return 0. So then for every row in the board, what we want to do is if we've already placed on that row, we know we can't do it again. So we're going to continue. Otherwise, we're going to say, we're going to add the row. Then we're going to say, I'm going to get from that row in that column, and then move on to the next column. Right, so let's, I'm missing up somewhere. 0, 2. Then we should column index something here. Oh, enter equals the, oops, this should be the max of the answer for that. All right, let's see what I get now. 0. Okay, still not great. 2, we get 15. 3, we get 3. Okay, so pretty good. Like these two cases are right, but this one for some reason is wrong. How did I get 0 here? So probably like 3. Oh, because I'm going. Oh, okay. And we also maybe we don't want to place one here, right? So then we can do column unmax score. I think this is going to be like way too slow, honestly. That's not right. Yeah. This is tricky. Okay, because so what I'm doing here is I'm kind of just assuming that we're always going to set one in the first row, right? So if we go back to our drawing, we could have more rows here. So placing in this first row might not be optimal at all. So we don't necessarily always want to pick there. So is this just like straight up backtracking? Like just try every possible combination? I don't know. So how would we modify this? All right, we could say we could either place it there or we could not place it there, right? So like this is, we could either place it or not place it. This might be too slow. I think this would fail. 1, 24. Right, so this would be like we are placing one, and here's we're not placing one. So I think we also need to keep track of the number of rooks. Right, so and number of rooks equals 3. Elif all index greater than board. Then we return, well, let's just return a really small number. Right, and I guess my thinking here is that we could get to the end but not have 3 rooks placed. So in that case, it's not a valid configuration. So here we're adding a rook. Here we are not. And then we're starting with 0 rooks. Did I mistype something somewhere? Okay. Okay, so we have 1, we have 15, and we have 3. So this first test case, I'm still not quite getting. Placing 1. So here, this is like we're placing on the board. Here is we're not placing on the board, right? So does each one have to keep track of its state? Like here, it's probably either, I'm thinking like, so we know they have to be on different columns. So if we could find the 3 max between rows that are on different columns. So like I'm thinking, so the constraints are low, right? Let's look at number 4, sin 8, yeah. If I can get this 6, I'd be very happy. So this is 500, right? So the constraints here are much lower, right? So we have a 100 by 100 board. Can we possibly try every configuration? Seems unlikely. Uh, Three. So I'm trying to think if we would ever get on the same column, right? So we're starting on column 0. We're trying out all of these and saying if we're occupying a row, we go here. like, maybe do I have to pass in my state? Like, could I just do 3 loops? I don't think I can just do like 3 for loops through here. Like, try every combination for 1, every combination for 2, every combination for 3. So it'd be like m times n to the 6. Try it. I mean, I2, J2. Let's give that a try. So I'm just gonna do like literally 3 for loops. So let's do for I1 in length of board for J1 in range of board 0 for I2 in range of board J2 in range. This is kind of crazy. Let's see. For I3 in range, length of board 0 for J3 in range. It should be board range of board 0. So I'll do if I1 equals I2 or I1 equals I3 or I2 equals 3. Continue. Otherwise, let's also do the same thing with the J's. So J, 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 J. Then we'll do answer equals max of the answer plus J1. Let's do answer. Let me just break this out a little bit. Max of the answer or board I1 J1 plus board I2 J2 plus board I3 J3. Return answer 4, 15, 3. Should I submit this? I mean, let's see what happens. I doubt this is going to get accepted, but you never know. Yeah, I figured. Okay. So, no good. Let's... So if even that is failing, then I feel like... Let me reload this and see. So yeah, very low acceptance, like 5%. Okay. So we can't brute force it. I mean, backtracking is kind of brute force, so we can't really do that either, right? So basically what we want to do is, I'm thinking, like, we want to find 3 columns, right? This configurations of 3 columns. Try every combination, right? So let's say we start with the first column. We'll say, okay, let's place one here, but that's backtracking. Just do not attack each other. So what do we know about rooks? So we know that rooks can't be on the same row. They cannot be on the same row or column. Does it make sense to just always grab the largest values, like in a greedy kind of way? So here, right, we're grabbing 9. So let's look at this grid here. If we can discern like a pattern. 1, 2, 3. We have 4, 5, 6. And then we have 7, 8, 9, right? So we grab 9, and this basically excludes all of these. Then we grab 5, that excludes all of these, and then 1. So in this case, it's like just greedy. We're just doing greedy essentially. So let's try this one. So -3, 1, 1, 1. Let's do -3, 1, -3, 1, -3, 2, 1, 1. Right. So we grab this max. This excludes these. Then we just want to grab another max, right? So the thing is, if we're greedily choosing the max, like say we had 2 here and we had 2 here, no matter which one of these we choose, we're excluding the other one, right? So that's what I'm kind of thinking. Maybe we could just like do 3, not nested for loops, but just 3 for loops, right? So let's do for I in range 3, do this 3 times. We'll say occupied is a set, and we'll do for I in range nums, or j in range of, should be board length of board 0. So we'll say if occupied rows, let's do rows, and then occupied if I in occupied rows or j in occupied and we'll continue, and then we'll do max value equals float infinity, our max cell equals 0, 0. So then we'll say if board I j is greater than our max value, then max value equals board I j, and then we say max cell equals ij. And at the end, what we could do is say what we could do is then answer plus equals board I. So 0, so 1, and then occupied rows. add x0 occupied columns add xl1. Right, and then we return our answer at the end. Oh, let's do our answer 0, -9. So not great. How would you get -9? Print max value. Print our max value. Oh, it should be -34. We have 15 and 3. My concern is that this is just a greedy approach. I'm not sure this is going to work for every case, but let's submit. Yeah, that's what I figured. So we have 82, 24, 11, 95, 91, 8, -89. So we expect this to be 144 as our answer, but I'm getting 90, 30. So I guess if I chose this one, and then that basically excludes all this, all this, and all this is crossed off, right? So then I'd probably pick 24. I would pick 24, and then I would be left with my max would be -29. So we'll see 95 plus 24. 95 plus 24 plus -29. Yeah. Right. So this greedy approach doesn't work. So probably what should have happened is that we chose 91, got rid of this, 82, got rid of this, and then -29. So it'd be 91 plus 82. 91 plus 82 minus 29. Right. Okay. So greedy doesn't work. So I feel like this has to be some kind of DP. So can I do like DP on the grid, maybe, and say like the maximum. Like, what if we did a DP thing in this grid where we're like, all right, so here, let's get rid of this. Like, what if I could, this is 24. Is there a way, like here, I can know the maximum value I can get, like how much I'd be excluding? Let's see. Still very, very low solves, less than 10%. Okay, so now I'm thinking like, what if there's like a DP way to do this? So if we know the cost of each row and column, right? If we each row and column, right? Like we probably want to pick ones where we're like removing least, right? So if we picked this, right, we'd be removing. So like we know we want to pick this one first. Let's move this over. Oops. Move this. Whatever, doesn't matter. Let's get rid of it. So if we're here, what if we know, like, if we remove this, we're potentially removing how much? We're removing 24 plus negative 30 plus 95 plus 8 equals, let's do the math. So over here, we have 24 minus 30 plus 95 plus 8. So this is 98. If we remove this one, we're removing 82 minus 89 plus 91 plus 8. So 82 minus 89 plus 91 plus 8. So this is 92. So does it make sense to remove this, right? Like, what if we knew this for every cell? We do prefix of the rows, prefix of the columns, and then essentially choose the ones that have the least cost. So what if we looked at, like, maybe another, what if we looked at 24? So we'd have 82 no, this doesn't quite make sense, right? Because we probably want to sort by, so let's just do 8. So we have 8 or 24. 82 plus 11 plus 95 minus 89. Okay, so 82 plus 11 plus 95 plus 89, 277. No, wait, this should be minus 89. This is 99. But yeah, that doesn't necessarily make sense because, like, we could end up choosing a negative. Like, if this was negative, we would still see this 99, but we'd be adding a negative number to it. So yeah, greedy doesn't work, so we know we can't do this. It's got to be some type of dynamic programming here of, like, what is, like, what if we did a prefix sum? So what if we had 3 rows equals this the default int, and then we had columns. I'm just trying to, like, see what the sums look like. It should be for range. I'm trying to type length of board. J in range board 0. You could do row we could do, hold on, row I plus equals board I, j, and we can do rows j equals board j. Let's print rows and print. Let's see what this looks like. Now. So let's look at this case. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So so this is, let's just put, we're dealing with sums. This is 6, this is 15, this is 24. This is 12, 15, 18. All right, so we know that we want to choose this one first. So if we do 24 minus 18 plus 18 minus 9 minus 2 minus 2. So this is just 24. Right, let's say there's another choice. Let's say 8. So if we had 15 plus 24 times 8 times 2. This is minus 8 times 2. Alright, so this is 15 plus 24 minus 16. So this is 23. Do we just want to pick then, like, go through 3 times, whichever one we're giving up the least? Like, does this tell us anything? It's basically saying, like, we know if we pick this, this is the amount that we're giving up, right? Because we could do 7, 8, 15, plus 6, plus 24. So we're essentially giving up this amount. So we're going to say, like, so how do we use that? Like, I want to say what's giving up the least, because if we want to say the least, it would be, well, we'd start here, right? This is giving up the least. Then it would be this, and then this, right? So maybe I want to try this case. Let's try this. Let's add a test case and see what we get. Right, so I get 82, 24, 11, 95, excuse me, 91, negative 8, negative 89, negative 30, negative 20. And then we see our rows are 117, 178, and negative 148. And then we have 88, we have 85, and we have negative 26. Right, so I think if we're just going by whatever is the smallest, that means that we would by default pick this just because this is negative. It has a negative column and row. Uh, yeah, so it's like something with like figuring the least amount we're excluding, right? Or like part of me says we want to prioritize the biggest ones, but we've already seen that that leads to answers that are wrong. Like we can't just do a straight greedy solution. Can we do the backtracking? Like maybe, but that seems like it would just be the same as the other ones, right? Or maybe we need to memorize it somehow. Uh, right, so we're still getting a wrong answer. We're getting 186 here, right? So this is clearly not right. Looks three. Okay, so see if our backtracking logic is still wrong because this one we're getting the wrong answer. So if we get out of bounds and number of rooks is 3, then we're good. Otherwise, we're saying, oops, if we're ever greater than 3, then we know that we're going to replace too many. So for each row, I got the right answer. Still getting 1 here. I'm not sure why I'm getting 1. It's very weird. It's greater than or equal to length of board 0. Translate infinity. So how would I even be getting 1? I have to be getting negative 3, 2. How would I even get that? Oh, because it's not, we're not placing it. Can I memorize this in any way? I'm not sure if caching is helpful here. I feel like that we might be caching the wrong answers. Yeah, that's what I figured. Let's just try to submit it. I'm not going to lose at this point. Yeah, it's gonna TLE. Okay. Can we do like digit DP maybe? Where we're like even that might be too small, like too big. Like if we have to yeah, it's gonna be some gigantic number. This is definitely a hard one. I feel like there's some sort of DP we could do like with the grid. Like, is there a way to know, like, with dynamic programming over the grid, which are the best spots to choose? So I think like if we did this, right, we basically say, all right, well, I'm getting rid of this. And then what I want to do is say, so we confirmed that 144 is 91 plus 82 minus 29 is 144. So maybe it is that, right? Because then next, what we would get is, so we have either 177 or 117. Yeah, so it would definitely be, no, but then we'd be choosing this. Like, if we eliminate these two, then we want to do this based off of, yeah, so if we do 117 plus 85 minus 24 times 2 versus 88 plus 117 minus 82 minus 2. So actually this would be less, right? Because we have 82 times 2, 164. So let's do 88 plus 117 minus 82 at 41. All right, so this equals 41, and then this 17 plus 85 times 24 plus 2. Oh, whoops, this is minus 118. So maybe that works. Let's see. Okay, so then let's put heap q, and we'll do heap, let's do for I range of board j and length of board 0 are going to do heap push. I'm going to do a min heap. So we want to do pre-calls j plus pre-rows I minus board I j times 2. So this is the value we're going to use in our heap. And then we're going to do I and j. And then I think our heap after this. and see what we get. Where is my heap? What do I do? I don't like this. Why is it like this? Okay. Why isn't it printing the, oh, that's why. Oops. Oh, it should be heap due to heap push. Heap. So the T argument's got 3. This whole thing in there. Alright, that's fine. So here we would pick -7, not right. Two, 1, 1. Which was not right because for 1, 0, we'd be getting 15 plus 12 minus 4 times 2. Wait, how? I don't understand. How is that possible? Oh, let's look at 2. So this is saying we want to pick 0, 0. We want to pick 0, 1. No, that's not right. I want to pick 2, 2. No, okay, that's not quite right either. Use the parentheses. See if that changes our result. 0, 0, 0, 1. No. 0, 0, 0, 1, 0, 2. So 2, 2. I'm going to pick 1, 1. So now we can't backtrack. So we need to find some way to know which cells are the best choice. So see, 2 is the first choice that we pick. And is that just because it's the largest? Well, you've seen just picking the largest is not optimal in this case. Because picking 95 excludes us from getting, right, so we want to pick 91, 82, 29. So is it like if you see a cell but that's just, I kind of think of a way we could do this without just backtracking. Like if we know the sum of the rows and columns, that is helpful because we know how much we are like giving up if we pick this. But we have to factor in that cost as well. So what if we also add the cost back in? Kind of just grasping at straws here. 0001. No. We want the max. We want 22, 21, 20. It's weird this just kind of like goes in order. And we want 1, 0. Do we want to just pick the positive numbers? No. So pick these. Right, so you pick 0, 0, right? Is that right in this case? Yes. So while we're going through here, we know we can't do any of these. So the next one has to be 1, 1. Let's see here. So we pick 1, 0, but that's wrong, because that excludes us from getting this 2. So we want 0, 1, 2, 1 is the one that we want first, right here. So maybe this method is not the right way. Like, what if we try to think if we could find the maximum amount? Like, what's the max if we place a rook there that we could get otherwise, right? Say we placed a rook here. It's saying we know we're excluding all of this and all of this. So let's look at the max. Like the max that we could get is essentially these rows and these rows, right? So what if we had a whole 0, forward IJ, right? And then we can do, instead of this, we do keep. So that essentially it's like pushing into the heap that value, so board IJ plus the sum minus P calls J minus 3 calls I, and then also just IJ. Right, so we get 1, 1, which is again not right. We get where's 0, 2? So 0, 2 is all the way at the bottom, right? So you get 0, 2, 2, 2, 2, which we can't do because it's here. 0, 3, 0, 3, which we can do, right? Then we come to 2, 0, which we can't do. 0, 0, we can't do. So we want, which cells do we want? We want 2, 1, we want 0, 2, and then we want 1, 3. So 1, 3 is like all the way back here. Right, so let's do rows equals set equals set, and we'll do keep keep I don't know, cost position. Right, and then we'll do, let's print the position if 0 in occupied rows equals 1. What we could do is say our 0, so our answer plus equals stored 0. And then we do for 9, which is that right? Nope, should be 15, 3, nope. Very, very, very wrong. Okay. Very, very wrong. Yeah, very, very wrong. 3, 15, 3, there's only 2. Yeah. This whole thing. Maybe just make it a max heap. I'm kind of just playing around with things at this point. I'm pretty sure I'm not gonna get this one right, but I'm just kind of like playing around, seeing, what I get. No, that's wrong. I'm thinking if it's like maximizing the diagonals. Like, what if you said, I am placing this here? No, doesn't make sense. Wow, this is a tough one. Really difficult. I think this number is higher than it should be. I think there's probably some cheaters in this contest as usual. Alright, so how do we... I think my main question is, how do we determine which cell is the best to place our rook in without backtracking, without doing some kind of brute force? I think we've played a lot with figuring out like opportunity cost. Like if we place a rook in a certain cell, we know what we're eliminating, right? But we can't seem to back into an answer from there. Right, because we could, like, that doesn't take into account our current position, right? So say, maybe if, say we take this cell, we eliminate like -3, -3, -3, which is probably the most. But this is also negative, right? So it's like, do we want to add this? Probably not. So maybe we need to do the backtracking, but we can't. Maybe like the caching is wrong. No. Just think of maybe there's a way you can backtrack a bit more like elegantly. Go back to this for a bit. Right, so here we're keeping track of the state. Trying to think if there's maybe a way we can like not do this. What if we knew like the maximum we could get from a row? Like say we knew the maximum we could get from column 1. We know that it is 2, right? We can say like the maximum is, what if I did this? So we have these pre-row columns. We say the maximum of this row is the total sum, like basically 0, or, right, but we still need to keep track of which rows we place our rooks in, which is the hard part. Does it kind of become like a divide and conquer thing, where it's like, if we place that's interesting. If we place a rook here, then that essentially becomes a sub-problem. So it's like, we could place a rook here, place a rook here, place rooks here, and place rooks here. That could be something interesting, because that's kind of like dividing into sub-problems, making it smaller. Right, if we place one here, we're essentially dividing it into this one sub-problem here. Then we also need to keep track of like the number of rooks we have. Yeah, unfortunately, I don't think I'm going to solve in this contest. This is a pretty tricky problem, but I will upload a video trying to show everybody how to solve this. So hopefully this was fun for you, was helpful, and thank you for watching.